explaining the point of the session. It's basically predictive maintenance and failure detection, diagnosis, and prediction. We know that while in the old days, reactive maintenance led to the expensive production time loss that we had when we needed to wait for the maintenance to actually take place. The next step was preventive maintenance with its problems having to do with suboptimally blind maintenance steps, in the sense of not optimally figuring out the maximal lifetime of maintained work parts, which led to predictive maintenance, which uses learning models to place the maintenance steps at just the right time. Various forms to include adaptivity, robustness, and context invariance of these methods are nowadays comprised in prescriptive maintenance. And this is a big topic of this conference. And for this, we start now with the talks. I'm glad to be able to introduce Ferdinando Chiacchio at the University of Catania, who's a research associate, and will talk about dynamic failure rate model of an electric motor comparing the military standard and the SKF methods.
Thank you, Mr. Chairman, for this opportunity. Thank you for the nice introduction about the main topic of reliability and maintenance. This research paper belongs to this umbrella agenda. I'm going to present to you some of the research that we are doing at the University of Catania about dynamic failure rate. Okay, so in this specific research, we try to compare two different methodologies for understanding, for showing how the modeling of dynamic failure rate is very important for such a subject, for such a matter, reliability and actions that concern the dependability, maintenance, and other action. Okay, so the main. I hope you guys see my presentation. I haven't. Yes. So the main goals of this research is to provide a better reliability model for one of the most important equipment in the industry, which is the electric motor. Okay, in order to improve the maintenance and also the inventory management of the components that are required to make an engine work properly. Okay, so spare components. We are proposing a comparison between these two different prognostic and model-based technique, so the military standard and the SKF method. And the third goal is to improve the usability of this library, the Shift2, that has been conceived a few years ago in my group, and to test the capability of the simulator. So I am one of the contributors of this research. The main research investigator that is studying the failure rate is not here, and I'm presenting on behalf. Okay, so basically the problem starts from the things that we have, as I told you, we conceived a new methodology, a new methodology that is called SHIFTA, stochastic hybrid fault-free automaton, that about a few years ago we started to use very, very largely in our industrial and research application. So this methodology makes use of stochastic hybrid automaton, combines stochastic hybrid automaton and fault-free analysis, and specifically dynamic fault-free. A stochastic hybrid automaton is a complex model that embeds both continuous and discrete states in stochastic and in the deterministic level. Okay, so the combination of these two let's say type of status creates a very complex and at the same time powerful modeling tool. Stochastic hybrid fault automaton made a step ahead, creating a combination of stochastic hybrid automaton and dynamic fault tree. This is very useful in the industrial application because it can simplify the models of complex industrial scenarios, and this allows a better investigation of reliability and in general dependability. So everything is good. This is some examples from the literature about stochastic hybrid automaton. Also application, for example, taken from the industry. This is a photovoltaic power plant model, and this is a fault tree. So everything is good and nice, but after using this powerful tool, we realized that the main problem with this technology is that what we miss is the information about the dynamic failure rate of components. So now we are able to make complex systems, okay? Complex methodology. We are able to simplify the modeling of complex dynamics, complex mathematics with the tools and with the methodology. But the main problem now is that we need inputs, okay? And in this case, we need input about failure rate, because as you understand, as you know, rate of a system change depending on the working condition and many other factors that we should take into account. In general, as you know, the failure rate are considered as constant because we assume that during the useful life of the component, we only expect a random failure. But this is, as you know, this is ideal and is not the real life. So the first claim of this research that we have taken in our research group is to understand better the importance of having more precise dynamic failure rate. And in this case, we decided to analyze the asynchronous motor, which is the main subject of this research paper. Of course, in this specific contribution, we have started to analyze the main components, mechanical, which can be affected by aging, deterioration, and that are affected by other environmental conditions like temperature and aging. Okay, so in this specific case, what we are analyzing is basically the windings and the bearings, which are, by the way, important component that you always need to have when you want to replace such components in an engine that has been consumed. Okay, so the main things is in this research. The main thing is that we try to understand both the contribution of these two main components and to create a model for the failure rate of these two components. And we used both the SKF model that you can find in the literature, in the manual of this company that has a lot of laboratory in Netherlands and in Sweden for testing bearings, but also the military standard, which is a old manual that has been conceived several years ago, that try to analyze how the failure rate change with respect to the working condition. So specifically, in the asynchronous motor, we have two types of windings, stator and rotor. And you can see that thermal aging creates an increase. So basically what has been seen is that an increasing of 10 degrees halve the aging, the life of the windings. So basically, we can see that depending on the temperature of the working temperature, the aging of the windings is higher. Okay, and this has to be considered when we want to analyze a motors and its reliability during this working condition. So this is the first claim. The other claims is about bearings. So bearings was the other components, and it has been found in the ISO a formula to calculate the general bearing life that can be computed according to this formula, where NA is the reliability that we expect to have, okay? And so with this formula that depends on many factors, alpha 1, alpha 2, and alpha 3, C and P, you can have a rough idea of the expected life of a bearing, okay? Of course, these parameters can change, and specifically, alpha 1, okay, is a corrective factor. Alpha 2 depends on the material on which this bearing is placed. And alpha 3 is a corrective factor that depends on viscosity and temperature, which is basically linked to the working condition. Of course, C and P, as you can see, are load coefficient, but also these can change in a working condition. So the age, the respective remaining useful life of a component is changing dynamically depending on the working condition. Now, in this work, we try to implement this formula and we try to create several simulation campaigns to understand how the working condition can affect this failure rate, okay? And what we want to show is that the formula proposed by SKF, which is correcting and coupling alpha 2 and alpha 3 because they are tightly related, and using a factor of correction in the parameter L, can have a formula which is a bit more complex and can take more information in it, okay, more than what the military standard proposed, because the military standard proposed a formula which is dynamic, that is true, with the change of temperature and cannot take into consideration the aging. So this is the two different failure rates that we wanted to compare. But to do that, as I told you, we needed to instruct a simulator model, which has been used to create a Monte Carlo simulation. And we provided some working condition, okay, and some other information that depends on the time, on the mission time, on the cumulative workload. And in this way, we compare these two different results, okay? So here you can see how we want to propose, how we want to carry out a Monte Carlo simulation. A time-driven Monte Carlo simulation is simply performed by creating equations of the failure rate with a delta t that is the integrated step. Of course, the smaller is the delta t, the higher can be the accuracy, but of course the time of computation can increase tremendously. So it's very important to find a time step which is compatible with the process that you are trying to model, but also with the time of computation that you are that you can accept. Okay. In the end, we provide these results that compare the military standard. You can see the gray line with respect to the other lines that have been computed using the SKF. So the main comparison is that the SKF can show the variation with respect to the equivalent dynamic load. Of course, this is just a picture because, for example, in this case, the failure rate is fixed with 450 of dynamic load. But with the simulator, we can also change dynamically the equivalent dynamic load. So this can provide to you also a failure rate that changes with respect to this important parameter, whereas the military standard don't have this possibility. Okay, so this is the first, let's say, result that we want to propose, we want to tell. The other one is the comparison of the same failure rate, keeping the equivalent dynamic load fixed, but according to a variation of, I think this one is the variation of temperature. It is not written, but The variation of temperature here you see has some modification of the failure rate for the military standard, whereas here you have more. Okay, and I think that here we are also able to consider the aging. I'm very sure that here we are also considering the aging, whereas in the military standard we cannot. Okay, so basically we started to discuss some formulation for handling a dynamic failure rate. This dynamic failure rate has to be used in our stochastic hybrid fault tree automation to improve the modeling of equipment, of important equipment, and in this case the electric motor. And we hope that in the future we can have more and more models that allow us to improve the knowledge of the equipment in such industrial device, and in this way we will be able to create more realistic model for analyzing the dependability and to know the remaining useful life of these systems. Okay, so it's very important. I think that also this topic, you know, we have presented a model-based approach, but I'm starting to think that data are very important, and now with the CPS-oriented system, so system that can catch, that can record data from the equipment, will be very important to analyze the condition and to make, for example, to understand how these components and they failure change according to the working conditions. So probably they can also be used to improve the models. So I think that in the future we are going through, in a type of study that will combine data-driven and model-based system.
Thank you, Ferdinand.
Complete. That's it. Thank you for your attention.
Thank you very much for this nice talk. Please, are there some questions? This is not the case. I would like to ask you, how much do the failures due to wear of the bearings that you observe come into play? So you gave several sources of a failure. Is the pure friction based wear an issue that you also include in the model?
Okay, so to be honest, we are not at that stage because we don't have, let's say, a laboratory where we can make such type of observation. So in this specific study, we are using two mathematical models that we can find, that you guys can find in literature. And in fact, we are trying to approach SKF, which is this important industry, with a lot of laboratory, to ask them if they can allow to study this bearing. So yes. Unfortunately, this part of the work is very theoretical.
Okay.
And yeah, so that's it.
I see. Thank you very much, Ferdinando.
Thank you very much. I think I can stop the sharing somehow.
Yes, I think it will just automatically go over to the next presenter, which will be Ms. Salma Mahmoud, a PhD student at Software Competence Center Hagenberg, working in predictive maintenance and explainable AI. She will talk about decay-parameter diagnosis in industrial domains by robustness through isotonic regression.
Thanks, Florian, for the introduction. I'll start sharing my screen. Can you see it?
Yeah, very well.
Yes.
Thank you.
Okay, so as Florian said, I'm going to talk about decay parameter diagnosis in industrial domains by robustness through isotonic regression. Let me go through the outline of the presentation. First, I will start by introduction. What was our motivation? What's the problem that we were trying to solve? And then give a little background about isotonic regression, which is the basis for our method. And then talk in a little bit in depth about our method and compare it to a traditional method that was usually used. And then a little demonstration of our results. So basically, in various industrial productions, they are concerned in their processes to determine whether something is out of shape, if there is some failures, if there is some anomalies that happens. And something that relates to this process is, or a part of this process is usually the warm-up phase or the burn-in phase. And this will be our focus of talk. And for the burn-in phase or for the warm-up phase, it's typically harder to know if there's some anomalies or not, because in the warm-up phase there is usually strong noise, because this is the part where the machine is just starting up, just warming up, and hasn't reached the normal process yet, or the settling time yet. Also, one of the problems that we may face is that we have to choose a scale-dependent parameter, and this provide limits and may hinder some usage for the naive methods that are usually used in this case. So basically, we propose a non-parametric method to estimate the parameter that's responsible for the exponential part or the warm-up phase part that precedes the typical process in an industry. So basically, as we see here, this is some examples from a drilling process, the warm-up phase of that drilling process. And each of these plots has different exponential parameters that we will call lambda. And so we basically here apply two methods. For the solid red method, this is the exponential regression, which would be typically or the simplest thing that you can use for such a curve. And for the solid blue line is our estimation that we use depending on isotonic regressions that I will later talk about. And if you can see, the little gray dots here and there are the data itself. And from this example, we can see that we have here the epsilon. This is epsilon isotonic, and this is epsilon, and the other epsilon s is the epsilon for the exponential regression, which use a smoothing parameter. And as we go from up to down, in each column you have the same data, and as you go down you have a different span, which is the special parameters that's used for the smoothing in the naive method, which is in red. And here we can see that typically our method, the blue method or the isotonic method, outperforms the other method, the exponential regression method. And we can see this from the epsilon, which represents the error, which typically we have a smaller error in most of the cases, comparing to the other method. So what is isotonic regression? This is the basis of our method. Isotonic regression or monotonic regression is the technique of fitting a free-form line to a sequence of observations under some ordering constraint of the fitted values. So as we can see here, the red dots is the data, and what exponential regression does is that it only can or stay on the same level. So it basically performs a shape of steps. And this is a comparison how it will look like if we applied it on this data. So the yellow line is the isotonic fit, and the blue is the normal linear fit, and the green one is the quantile regression. Also, isotonic regression should fulfill the condition of least square residuals. And yeah, so what is the relation of isotonic regression and robustness? So as we can see here from the first plot, isotonic regression is not so robust to some types of outliers, but if we apply this, if we have these outliers in the downward or on the concave side, we can have better results. So basically, as a comparison, if the outliers are upwards, it performs a bit worse than quantile regression. So if it was 10%, as we can see here, the RMSE is 0.08, while in quantile regression it's 0.07. However, when it's downwards, it outperforms the quantile regression. So we can say it's robust against outliers that's observed on the concave side. So what is our method, and what's the naive method? Our method is the isotonic regression method. As a first step, we perform isotonic regression on monotonic data, and then we cut off the first part and use values larger than 0 to compute the logarithm and to transform the data into linear. And after transforming the data into linear, we now can apply linear regression and to estimate the parameter, which we will call lambda ISO, as the regression coefficient. However, the naive method that was typically used differ from our method in the first step, where instead they apply a smoothing filter, for example, the LES smoothing filter, where you have to choose a scaling parameter for this filtering. Second step would be also to use, of course, values that are larger than 0 in order to compute the logarithm. And then finally, you also apply the linear model to obtain the estimate of the decay parameter, which we will call here lambda exponential as a regression coefficient. So as for our results, we applied the algorithms over synthetic data to allow a systematic performance test. And here we have different values of lambda, which we want to estimate from top to bottom. And we produce the data with also some additional noise, which we will call sigma, that differs from left to right. And for each column here we have the naive method 1 as the first column, and then the naive method 2, which considers the part that is larger than 0. And then the isotonic regression, which is our method, is in the third line. So our main comparison would be between the naive method 2 or the exponential regression 2 and our isotonic regression method, which is the second column and third column. So we can see, for example, in the first upper left plot, we have the estimation for the lambda, which is 0.01. Both all of the algorithm can determine this well. And then as we go downwards, for example, the last plot on the left, we start to see that the first method doesn't even apply at all, and the second method is not so good, or at least worse than our method. So our method gives an estimation for the lambda as 0.071, and the lambda that we want to estimate is already 0.075, while the traditional exponential method has a lambda of 0.055. And we can see this throughout the different experiments that we carried on with different lambdas and different values of sigmas. So as a conclusion, isotonic regression was superior in performance in comparison to the naive regression method, which includes prior parametric smoothing, and increase in range of scale of applicability yields robustness against variability of the occurring settling time length. So although isotonic regression was not so robust in some cases, as we showed earlier, when we have typical anomalies in the upward direction, it's, however, benefit us that it is non-parametric, so it can be applied on a different range of scales. And yeah, that's it from my side. Thanks you for your interest.
Thank you, Salma, for this very nice talk. Please, are there any questions? Since I also was part of this project, I would, instead of asking Salma, like to ask into the audience, and you can just answer by raising your hand. If you have any applicability for testing run-in period settling lengths, please raise your hand if you could imagine that you could actually apply such a method in your project.
That would be also my question. It was a bit theoretical.
Okay.
And is there some application where you can use your isometric regression where it excels? Because you say that it's only a certain area of the data. So when is this the case, or is there an application where this is always the case, so you are excels in every way?
I mean, Salma will tell you it's applicable wherever the exponential regression is, and even beyond that. So the results shown were actually data taken from a production process that involved measuring the drilling speed of a drill that starts being used, and until the stationary production mode is reached, the settling time is measured. So this is precisely the data you have seen, and which will be in the paper. Perfect. Thank you. So we should now pass on to the next talk. I would like to ask Lukas to give you a presentation now. I have learned at University of Applied Science. Your talk is going to be about the research of context and an Industry 4.0 data set of contextual faults in a smart factory. Thank you.
So thank you very much. No, that's the first time I work with MS Teams, so I try to share my screen.
Mm-hmm.
I think I got the wrong one.
No, well, I see. We see it. You may have shared not. I mean, we do see your.
I shared the wrong screen, I think.
Try it again.
So hopefully, no, it seems right.
That's good. Thank you.
So, okay. Hello together, it's a pleasure to be here. My name is Lukas Kaupp. I'm a research associate from Darmstadt University of Applied Science. And today I will talk about context and Industry 4.0 dataset of contextual faults in a smart factory. So here's our team. Myself, Heiko Webert, is a specialist in automation in Industry 4.0. Kavan Asemi is a specialist in visual analytics. Bernhard Hung is specialized in applied artificial intelligence, and Stefan Simons is specialized in automation in Industry 4.0 as well. Before I go into detail about our findings, I will show you the assembly process in our smart factories that was recorded in our dataset. First, the robot takes unassembled parts out of a high bay storage onto a shuttle system. Next, it gets assembled by a 6-axis robot. The press assures, after that, the press assures connectivity between the relay and its socket. In the end, the electrical inspection proves the functionality of the relay. In the end, the proper function relay will be stored back in the high bay storage. For the time of recording, the optical and weight inspection station was out of order and therefore not recorded. So what was the motivation behind our context dataset? We have the use case of fault diagnosis within a complex environment with external systems like ERP and MES, cyber physical systems, internal and external sensors, actuators, and a lot of customized communication and proprietary protocols. Furthermore, we are in a transition between states, between Industry 3.0 and Industry 4.0, with a lot of brownfield machinery and cyber physical systems working side by side. And we have, or I call it, fenced machines, where we have a lot of internal data that is not communicated to the outside world. So fault diagnosis in a smart factory has to deal with big complex data and even hidden information. The major purpose of our context dataset is to showcase our contextual faults. In our opinion, the context matters in such a complex environment, where you have so many interconnected machines and data involved, so you need some sort of context to set outliers into perspective and find a reason for the fault. So we defined the contextual fault as an invalid and unexpected value within the attribute context of a CPS. It's a rounded context, a global production line context. As a result, we have context hierarchies around machines, around machine boundaries, or the whole production line, here represented as context level C. We already defined our context in a previous publication. A context is a window around an outlying timestamp plus minus x. Plus minus x can be set by a domain expert, and the window is overall available information sources. Here, process information and CPS information in this case. This allows us to automatically detect and extract the context and use it to our advantage in future. So our recordings are based on two different information sources. So one instance is the OPC-UA server, and the other are our industrial Internet of Things. Here I will talk about the OPC-UA recordings. We have a machine execution system that operates the smart factory, the high bay storage, the assembly robots, the press, the optical and weight inspection, and the electrical inspection safety. As I told you, the optical and weight inspection station was out of order for the time of the recordings. Nevertheless, we have about 30,000 OPC-UA variables that we can subscribe to, with interesting data types like byte strings and S bytes, and also Boolean values, which can be an unexpected array string. So it's like in the very real world, you should not do it, but it will be done somehow. So the log structure is pretty simple. A datetime string followed by a node ID, which covers the origin of the message, dot separated, the value, and the data type in one line. On the other side, we have our industrial Internet of Things. On the upper right, you can see our Shuttle sensing unit. We employed multiple sensing units throughout the smart factory. Sensing unit consists of an Arduino processing unit, here a TNC 3.6, an I2C multiplexer, and a sensor group of 3 sensor types: motion, light, temperature, and pressure. The motion sensor is an MPU 9250, the light sensor is a TSL 2591, and the temperature and pressure sensor is a BMP 280 from Bosch. As you have may noticed that these sensors do not have or rely on any industry standards, so they are very low budget. They are cheap to obtain, to employ, and to replace. But in the end, fully exceptional to detect our contextual faults that we have recorded. The log file structure is all numerical with the schema sensor type _ metric. Our context dataset consists of 4 scenarios: the normal operation, aka our ground truth, the shuttle dropout, where the shuttle is held in the manual inspection station, so the production output is cut in half, the missing parts where the robot tried to assemble air, and the missing pressure where the production process slows down. This dataset allows us to showcase our contextual faults that we think are a major problem in the smart factory in the future. So we can use this dataset to develop algorithms for it today, so we can use them tomorrow. Here you can see our ground truth. The data encompasses the assembly of 16 relays, 8 fully functional, 8 faulty. Therefore, there are two cycles, one with functional relays and one with broken parts. This comes useful later. At the upper right, you can see the activity of the robot sensors during the assembly, and the 8 blocks of assemblies. One block consists of 2 stations. The green window shows the tool grabbing procedure of the robot, and while the yellow window shows the assembly activity. In our pressure use case, the pressure is lowered over time to a minimum operation level, where it is re-established after the pressure leakage is fixed. This can be seen in the acceleration data over the electrical inspection, upper left, data upper right, where you can see a spike if the sensor is shadowed and lighted again quickly, whereas the motion slows down, the spike becomes more a curve because the sensor has more time to adapt. The benefit in detecting such a use case is to prevent production slowdowns and a possible downtime. The shuttle dropout is very straightforward. After 2 successful assemblies, 1 faulty relay will be produced and the shuttle drops out. After 5 successful assemblies, the shuttle is queued back and 8 faulty relays are produced. The key benefit is that we can keep the production output high if we can detect this case. In the missing parts use case, the first successful cycle takes place and the part starts missing in the faulty cycle. So it's harder to distinguish between a faulty relay and a missing relay. The output stays the same. The relay will be sorted out in the manual inspection area. So this can be seen if the robot grabs air. A spike can be seen in the acceleration values on the upper left and in the OPCVA data on the upper right of the press, where you can see an increase in pressure after each time the press presses air. If we are able to detect this use case, we can reuse the faulty tag parts in other relays, and therefore we can minimize the waste and environmental impact of the production. So our contribution is threefold. We give a first definition of contextual faults. We name examples and use cases like shuttle dropout, missing parts, and missing pressure. And we open source our recorded dataset on Zenodo. So everyone and everybody interested in can download it and investigate over 2 million log events further. To come into an end, suggestions and additions and improvements are very welcome, and we have now time for questions.
Lukas, for this great talk. Are there any questions?
Me? I have
Yes.
one question.
Yeah.
Okay, my name is André Martins. Thank you for the great presentation, Lukas. You talk about the use of OPCUA at some time in your presentation, In what way you use this standard? Can you provide more details?
Yeah, for sure. That's not a problem. I use the title, the free OPCUA Python implementation library, and record each cycle with a separate script. So you can pair each cycle of the recorded data. Yeah. And in the beginning, first of all, I scraped the whole OPCUA server for all subscribable variables. These 33,000 variables are only the nodes that you can subscribe to. So we have more nodes, but they are not every. You cannot subscribe to every node. So
okay, yes. Okay, but in a publish subscribe approach or server client classic approach?
So yeah, that's a good point. Well, I only subscribe to event change events, so I cannot subscribe to all nodes together because it's only 100 megabits, and the whole smart factory explodes if I do that. So I only choose to subscribe to the change events, and I only get the change events in the smart factory. Okay,
thank you for your answer.
Thank you for this interesting question. Are there any more questions? Lukas, I would like to ask you, you were talking about this hierarchy that yes. Comes from the definition of context-dependent faults. To suggest, do you observe any trends in terms of the different faults that occur where you can say, well, typically faults that arise, for example, from local misconstruction of the assembly line, for example, let's say stick slip effect due to lack of lubricant, yes. Occur on a different level than a different type of fault. Can you experience such trends?
Yeah, this is a really good question. Thank you. Well, this is part of my current research. So we published the dataset up front, so we can use it in our future publications. And currently, we're looking into the context dependencies and which algorithms we can use to extract the dependencies within contexts and the relationship between contexts. So we can answer your questions hopefully in the next half year.
I see.
More clearly.
Thank you. Mm-hmm. Very interesting. Are there any more questions? Okay, this is not the case. Then thank you again, Lukas. We will now come to the next talk, which is the fourth contribution. Since this is the last speaker, I would like to use the opportunity before everybody runs away afterwards to encourage using the interaction rooms. So if you like to connect and speak to other people, don't forget we have this opportunity by hanging out, so to speak, virtually in these rooms. And now I would like to use Dr. Sathyan Munirathinam from San Diego. He is working for ASML, if I am correct. And this is a company producing EUVL lithography lamps, and I think I shouldn't say more and let him specify what I'm trying to say in this introduction. Please, Dr. Munirathinam, for your presentation. Thank you.
Thank you. Can you hear me?
Yes.
Okay.
I can see it also very well.
Thank you so much. Good morning, good evening. I am Sathyan Munirathinam, working as a solution architect manager for ASML. And most of the people should know that ASML is the largest semiconductor equipment manufacturing. Specifically, we operate in the photolithography space. So I think that all chips made out of this very sophisticated equipment component that we make, and we are proud of it. So today I'm going to talk about drift detection analytics for IoT sensor in the manufacturing facilities. Quick agenda for today. I want to set the stage, understanding the semiconductor manufacturing process and the problems that we face in this highly sophisticated manufacturing process. Most often, the industry operates on a primitive way of monitoring this equipment using called a statistical process control, or in a short form called SPC limits. The major flaw in this monitoring system is unable to detect drifts within the static limit of, and upon triggering of those limits, it's usually too late for the manufacturing team on the floor to take any preventive actions before the system really goes down. So we developed a more of a generic model for detecting drifts within the limits and identifying potential outliers. We used called a double linear regression model that identify both aggressive and progressive drifts. And also we used adjusted box plot method to detect outliers in both symmetric and skewed distributions. That's a quick agenda. So let me go to the problem statement. I think that will help what we are talking about today. If you look at the equipments that we talk about in the semiconductor industry, it's pretty expensive, right? Any equipment we talk about, like take about the photolithography equipment, that's almost cost each equipment $5 to $10 million. So any downtime of those equipments will have a severe impact in both the productivity of those chips making and also hitting the customer demand. And also it has other implications of the downtime if anything goes from a 1 hour to 2 hour or anything more than that, right? So that's what we want to address. How do we notify the technicians or the engineers to act proactively and then start working on it before it really abruptly goes down? So we use called, I think this is more of an industry 3.0, right? If you will, it's more of a SCADA. That's a precursor of an industry 4.0, supervised control and data acquisition. Most of the manufacturing facilities operates on the SCADA with the PLC devices, right? All the hardware equipments connected through PLC. And then we have a lot of sensors connected to that devices. It can be a vibration, acoustics, thermal pressure, gas flow. It's all installed in the manufacturing facilities. And then we collect the data from the SCADA databases, and then we run through all kind of machine learning algorithms to come up with some sort of trending how well the equipments are working, right, in terms of understanding the health of each of those equipments. Okay, so I think I'm going to talk about a specific equipment. That's why we deployed this algorithm, and we've seen a lot of values coming out of those tools. Right. So if you look at the semiconductor manufacturing, clean room is one of the important aspects, right? It's the 1,000 times more cleaner than any medical operation room, to be precise. So in order to maintain that specific sort of a very sophisticated requirement, we use so-called called a clean dry air compressor. That's a massive equipment unit, which has all things goes on within that compressor itself. So we want to monitor that specific compressor by installing multiple sensors and then collect the data and then understanding the overall health of the equipment itself. So if you look at the chart, the sensor chart, you can see all sort of data that's coming out of that tool, and you can see that the sort of an SPC will not fit into this controlling this chart itself. So I think our research comprises of two things. One is more of an infrastructure, and the second one is pretty much on the software or the machine learning approach, right? So what we come up with is called a super sensor. So if you look at in the manufacturing facilities, we cannot install multiple sensors. Each sensor should have and their electrical outlet. They need that their specific network outlet, which is not possible itself, right? In terms of bringing all the wire back to the back-end facilities and install, that's not really practical. So we come up with this sort of called a super sensor, where we put all sensor peripherals in a single PCB board itself, right? So that one outlet, one network should be enough to feed this whole suite of data flowing into the one pipe, instead of having a separate sensors disconnected from here, and then data flowing into the system itself. So we put all the into one system, and the data goes there. So all the way from a temperature, the pressure, humidity, the vibration sensor, or the heat that generates from this compressor, it all flows into a single pipe, and that's why we use the data to run through our machine learning approach. So if you look at the goal is, so it's kind of a human app sensors able to understand the context going on within any space, right? That same approach, we want to come up with more of creating a smart context-aware manufacturing facilities at a snap. At a given point of time, we should be able to tell, hey, we have all things, components are working well, right? Do you see any problem going on? So if you look at the, we put a chart here, it's pretty much became the eyes and ears of the manufacturing facilities. So we have installed multiple this PCB boards in multiple locations, and it's really watching 24/7 and giving this real-time data to see how well each of those units are performing. So that's the more of the hardware side of it in a very high level. But if you look at the statistical process control, so what we generally do, the primitive way of monitoring those equipments is more of using a statistical process control, right? So we take a month or a 2-month, average it, and then we put some sort of a 3 sigma, 2 sigma, or 1 sigma deviation, and see if anything goes beyond that, and then we flag to the technicians, look at if this is going outside of the boundary, and then they look at the data and see what's going on, right? But the problem with this approach, the major flaw with this system is unable to detect drifts within the static limit, right? It can go to the boundary very quickly, and there is no time for us or the manufacturing team to take any actions. So we want to detect, or we want to notify the engineers before it really reaches the threshold limit, so that they have some sort of a time room to react. So that's the whole idea. So if you look at a little more understanding, what we're talking about is what we define as aggressive drift, and also it's kind of a progressive drift. So if anything happens within a short time, we call as an aggressive drift. And also we call as a progressive drift that happens a long term, that happens, right? It can be both down or up, right? Both drift can happen in either way. So that's what we want to detect. And also the goal is how well it's progressing, right? So we want to set a different threshold limits within the drift. Hey, this is more of a warning. Hey, this is more critical, so that the technicians can react based on that sort of severity. Okay, so what is a double linear regression model? The goal is we want to find some sort of a deviation. We use some sort of a slope from a steady line. Anything that drifting have some sort of a slope that goes beyond from the steady line. So we use some sort of an angle that determines the drift, and the angle tells us how well it's a progressive or more of an aggressive drift, right? So that's kind of the very high level algorithmic approach that we use. So if you look at a little more on the closest tip, so we use 3 days and a 7 days approach. From a 3 days, we look at 3 days data and come up with some sort of a slope, and then we use that as more of a baseline, and then we look at as a 7 days that also acts as another set of a baseline. That 2 lines will help us to determine how well it's really moving the data itself. right? Sometimes the data comes down or goes up, but it may be rectified. Maybe looking at the 7 days, maybe it'll be drifting down, but in looking at 3 days, maybe it would have been corrected, right? So that's kind of more of that's what we call as a double linear regression. That will help us to see how well it's really progressing the health of each of the equipments. So the next one we want to talk about is, I think maybe it's within the limits, or maybe it's progressing, but there are some sort of an outliers that we want to detect. So we generally box plot is the standard approach that we use to put some sort of understanding the continuous data distribution, right? But what we want to use some sort of a skewness adjustment box plot, which will take into account all sort of skewness in the data distribution, and also in terms of the data coming too much in some real time, we want to have more of a fast detection tool, right? We don't want to wait in the real time for data decision making. So we want to make it more of a fast decision making. So the last one is more of a severity score algorithm, meaning that the drift can happen, can go up and down, but still we want to understand how well the severity, right? So we model based on the, we took this from a medical terms, more of a call injury severity score. If anyone happens in the accident, they use some sort of a scoring and understanding how well we need to treat the patient, right? So that's the same thing, the same model. We want to put some sort of a severity score. Yeah, I think this is drifting up, but it's not that severity that we need to really focus on. More often a warning. Maybe if the score is beyond that threshold limit, then we can really focus on the specific issue, right? The two things it really scores is based on the change, how well it really goes up, and also how well it really, the duration of the drift plays in the determining the score itself. Okay, the future work, right? There are a lot of things that still we need to address. If you look at in the current algorithm, it uses each sensor and then we come up with a model. But what we want to move from a univariant approach to have a multivariant, right? How do we combine every sensor and then come up with one score, a kind of a health score, and say, hey, I think this specific dry compressor is in a pretty good shape, right? We don't need to really worry about how do we come up with that one. The second one, how do we determine the remaining useful lifetime, given that health of the indication, and say, I think this should go to maintenance in another 3 weeks or 4 weeks, right? So that's what we want to come up, that sort of an approach. The next one is we want to come up with some sort of a correlation. If you look at the in a semiconductor or any manufacturing facility, we'll have a downstream process, right? If this equipment has a problem and it has an impact to other tools in the chain, right? How well we will able to correlate? Yeah, I think we have a problem here. Can we determine the correlation to the other drifts in the detection process? The next one is that's why I mentioned of a predictive modeling to come up with determining the prediction of this health given the drifts that are happening within the tool itself, right? If the drift is really aggressive, then we will know that I think there is something going wrong in the equipment. So we should be able to determine that kind of a predictive ability within the tool itself. That's it, my presentation. Thank you so much.
Thank you very much, Dr. Munirathinam. Are there any questions? I would like to ask if you have considered using this method that you have, this double regression method, for instead of finding the slopes, also finding the interfaces between the regions of constant linear trend, namely for change point detection. It seems to me also important to know, of course, when the events occur, that there's a qualitative change in these curves that you have shown.
Yeah, that's a good point, right? The change point detection we looked at, but the challenge with that one, it's pretty very in terms of time-consuming process, if you will, right? Because we need to understand every distribution of data with the amount of data that is generated from this thing. We want to make it the runtime faster. Maybe that's a main reason we moved away that sort of an algorithm. I think I'm happy to share. I think we put some sort of results that what we call as a breakout detection algorithm versus our double linear regression algorithm. I think it should be in the paper. But if you have anything specific questions, I'm happy to answer it through my email. But I think we put the differences of those two methods.
Lukas, you have a question? Thank you very much. Thank you.
So, hello. That's cool that also ASML considering the same sensors as I do in my smart factory. Interesting to see. How is something or was something done against the normal sensor drift in these cheap sensors that normally appear? So normally if the sensors warm up, you have some sort of sensor drifting through recordings, as I have noticed in especially in motion sensors or in the light sensors.
Yeah, I think that's a good thing. That's what we also looked at, because if you look at this sensor, it's all piping to the same channel, right? So some of the sensors have a high frequency bandwidth sensors that generates a huge amount of data, right? If you take the thermal camera, that the density of data that comes in from the sensors is pretty much. So I think for that process, I think we have a 2-channel that's coming from this data. I think we put a low frequency and a high frequency sensors we grouped as 2 set of sensors that we want to deal with those set of sensors. We don't want to mingle those sensors, and it's hard to really collect the data in a real-time fashion. So if you look at, I think I didn't really get into much details here, but I think that's what we did as some sort of a grouping of the, like if we take an acoustic sensor, thermal camera, those are very high because it's all 48,000 samples per second or 48 kilohertz per second. That's a huge volume data that's coming. So that's coming through a different pipe than the low, like if you take a pressure sensor or humidity sensor or a temperature, that's very, I think it's just 1,024 measures per second, right? So that's what we dealt with.
Okay, thank you.
Are there any more questions?
Yeah, I have a question.
Please.
It is actually close to the question that has just been asked. It is about the frequency of the data collection, as this data is very huge, and there is a big amount of it. And also, I would like to understand what is the methodology to collect this data in terms of which format with which format did you use to collect this data? I mean, Excel or JSON format or etc.
Yeah, that's good question, right? I think we do. I think maybe I'll get a little more detail. So right, so this sensor we connected to more of an called Odroid. It's kind of a mini computer, right? That sits on top of this one, and then we run pretty much the Python streaming program within that Odroid board. If you look at all the data that's been connected to each of these devices, so we use JSON files, and also we use called a binary JSON, right? Because we don't want to treat as pretty much of the text, which is pretty huge. We want to compress as much as we can. For instance, like audio, we want to see how much we can we take as a WAV file, but we want to make it as a compressed, more of an MP3. But I think we lose some of the resolutions in the data. But I think at a over high level, that should be able to encapsulate all the deviations in the data, right? So those are the compressions that we did at the edge of the device itself. And then we do some of the manipulations within the device itself, right? If you look at the hardware configuration of the ODroid, that itself a pretty high beefy server. We have a 4 cores, and then we have a NVIDIA GPU that's running within the ODroid itself, right? What we want to do more of an edge analytics there itself. Yeah, I didn't put it here, but I'm happy to share a little more details in what we did on this specific one. Yeah, the two things, right? Obviously the compression and also the binary format of the data itself that we want to transport from the edge to the more of what we call as a fog or the middle server, central server of more processing.
Thank you. Any further questions?
Yes, I've got a question.
Please.
According to the training and testing on the slides, I think there was that you trained per days, and the testing there was hour intervals, and I kind of didn't manage to get why using by the training you use days intervals, and for the testing the hour intervals. Isn't this then a different? This should make a difference, shouldn't it?
Oh, okay. So I think so for this hour for testing, we want to pretty much kind of what we call enlarge that specific pattern, how well it's really performing within an hour, right? Because the drifts can happen not only within the days, but it can happen. For instance, we have if you look at we are running in a fab. In the cold season or a winter season, it can have a lot of amplifications in the temperature or pressure sensor, right? So we don't see in a day itself, but it can vary within an hour itself. So this is more of an enlarged section of within a day itself. We did a testing in the overall day, but we want to take a slice of every hour within the day and see how well it's able to perform within the hour itself. Is it meaningful or?
Okay, I think and I understood it now that you used it both. You trained your model on the days and also tested it at days, and then also tested it for hours to see how it performs.
Exactly, right. I think that's what. Yeah. So this, when I say enlarged, I think the testing it's pretty much focusing on the specific hour and see. I think it's able to detect drifts. Within an hour also. It's not really looking at the overall trend for a day, but it's able to see the trends within each hour also. That's what I want to say here.
Okay, thank you very much.
Great. Our time is coming to an end. Dr. Munirathinam, sorry, has pointed out that it may be so that people would like to continue discussion in more depth beyond this scope. So let me offer you to, if you have a question to anybody else in the session, go ahead and I will remain in the session. You can tell me, and then I will inform the corresponding person, and then you can talk about this in the virtual rooms that we have for this kind of thing, so people don't miss each other when leaving the room. So don't hesitate to talk to me as you walk out. And thank you very much to all the speakers. And I hope there will be some interaction and further discussion about this interesting topic. Thank you very much.